Good morning, everyone. My name is Shady Saeed, and this is the final capstone presentation for NutriScan, developed as part of the Master of Data Science at Deakin University. NutriScan is an AI-powered food classification and nutrition intelligence platform. The core idea is simple. A user takes a photo of a meal, the system detects the food region, classifies what food it is, and ultimately connects that prediction to useful nutrition information. In this presentation, I will walk through the business problem, the solution approach, the modeling decisions, the main insights, and the recommended path from proof of concept to production. The project uses 16,256 food images across 17 classes. The detection-first pipeline achieved a 93.5% detection rate, meaning most images could be cropped around the food region before classification. For classification, the strongest model result was 55.6% test accuracy using ResNet 50 with transfer learning, while EfficientNet B3 achieved 52% with a lighter architecture. Importantly, these results were achieved on a CPU-only laptop without GPU acceleration. That matters because the current performance should be interpreted as a validation, not the final performance ceiling. The strongest takeaway is that the pipeline works, transfer learning is essential, and the production risks are now clearly identified. The business problem is the failure of manual food tracking. Most diet and calorie tracking apps require the user to search for food, enter quantities, estimate portion sizes, and repeat that process multiple times per day. That creates friction. The user may care about their health, but the process is too slow and too repetitive. NutriScan removes that friction by replacing typing with vision. The user simply takes a photograph. From a business perspective, this is valuable because lower friction means better engagement, better data capture, and a stronger foundation for personalized nutrition services. The opportunity is not just classification accuracy. The opportunity is behavioral, making healthy tracking easy enough that users actually continue using it. The solution architecture follows 4 stages: snap, detect, classify, and advise. First, the user captures a meal image. Second, YALOV8N detects the food region and crops the image. This is important because food photos often include background noise, plates, tables, cutlery, hands, wrappers, or restaurant lighting. Cropping helps the classifier focus on the food itself. Third, the classifier predicts one of the 17 food categories. In Milestone 2, I tested 3 classification approaches: a custom CNN baseline, ResNet 50, and EfficientNet B3. Finally, in a production system, the food class would be linked to a nutrition database, allowing the product to return calories, macros, and recommendations. The pipeline is modular, which means each component can be improved independently. Before building models, the data analysis revealed the risks that shaped the entire training strategy. The first risk was class imbalance. 16 classes had 1,000 images each, but Apple Pie had only 256 images. That creates a 3.91 times imbalance ratio and means a model can perform well overall while still failing badly on Apple Pie. The second risk was detection quality. The detection pipeline achieved 93.5% overall, but 6.5% of images required full image fallback, meaning no useful crop was found. The third risk was the color profile. Food images have a strong warm tone bias, dominated by reds, yellows, and browns. These findings were not just descriptive. They directly drove the modeling choices: augmentation, ImageNet normalization, class-weighted loss, weighted random sampler, and per class F1 reporting. The modeling strategy was designed as an experiment framework, not just a model-building exercise. Each model answered a specific question. The custom CNN asked, "Can we learn food features from scratch using this dataset?" The answer was no. It gave us a weak but useful baseline. ResNet 50 asked, "Does transfer learning help?" The answer was clearly yes, because pre-trained ImageNet features provided a major performance uplift. EfficientNet B3 asked, Can we maintain strong performance with fewer parameters and better deployment efficiency? The answer was also yes, although in this run it did not outperform ResNet 50. Another important constraint is that all of this was executed on a CPU-only laptop, with limited epochs and batch size 32. That makes the modeling results conservative. With GPU training, longer fine-tuning, and more extensive hyperparameter search, the performance ceiling is likely higher. The model results show the impact of transfer learning very clearly. The baseline CNN achieved only 9.8% accuracy and 6.4% macro F1. That tells us that training from scratch was not sufficient for this dataset size and compute setup. ResNet 50 achieved 55.6% accuracy and 56.6% macro F1, which is a major improvement. EfficientNet B3 achieved 52% accuracy and 53.2% macro F1. The most important comparison is not ResNet 50 versus EfficientNet B3. It is transfer learning versus no transfer learning. Transfer learning delivered more than a 42 percentage point uplift over the CNN baseline. Because this was achieved without GPU infrastructure, it validates the business case for investing in the next stage. Cloud GPU training, more epochs, stronger tuning, and expanded food domain data. The deeper insight is that total accuracy hides class-specific risk. Pizza performed strongly with the best per class F1 at 82.4%. That makes sense because pizza has distinctive geometry and a direct visual structure that both detection and classification handle well. French fries are different. They are visually low contrast, scattered, and detection limited. If detection quality is weak, classification quality is also constrained. The cake family, apple pie, chocolate cake, and strawberry shortcake, creates a different challenge: visual ambiguity. These classes share circular shapes, layered textures, plate presentation, and similar colors. For a business leader, the message is simple: we should not deploy based only on overall accuracy. A safe product needs confidence thresholds, per class monitoring, and user confirmation when the model is unsure. My recommendation is a phased roadmap. Phase 1 is a limited beta using the current 17 class model with confidence gating. That means the system should only provide a prediction or advice when confidence is high. Otherwise, the user should be asked to confirm. Phase 2 is to replace the general detector with a food domain detector trained on datasets with food bounding boxes or segmentation masks. Phase 3 is class expansion, moving from 17 classes toward at least 200 classes and eventually mixed plate recognition. Phase 4 is full nutrition intelligence, portion estimation, nutrition database integration, user profiles, and longitudinal tracking. This roadmap turns the capstone into a product learning loop. It reduces risk, controls user expectations, and lets real engagement data guide where engineering effort goes next. The final conclusion is that NutriScan proves the technical pipeline works, but production success depends on closing known gaps. The most valuable lesson from the capstone is that data understanding comes first. Milestone 1 identified imbalance, detection limitations, color bias, and production gaps before model training began. Milestone 2 then showed that transfer learning is essential, and that per-class evaluation is necessary to expose hidden weaknesses. Another important lesson is that lean compute can validate feasibility. Building this on a CPU-only laptop helped prove the concept before committing to GPU infrastructure. The next step is not to claim the model is finished. It is to scale responsibly: better data, food domain detection, GPU training, portion estimation, and confidence-controlled deployment. Thank you. I'm happy to take questions.